So we have special names that are given to massive exoplanets. They're known as Jupiters, and these are things about the size of our planet Jupiter. Less massive ones that are up to about 0.1 Jupiter mass, these are referred to as Neptunes, and they probably have a substantial rocky core. From 2 to 10 Earth masses, these things are referred to as super-Earths, and below 2 Earth masses, we would call these things Earths. Now, your book says that there are no Earths that have actually been found. At the time the book was written, that was probably true, but it's no longer true. There were probably 3, maybe even 4, certainly at least 2 exoplanets that are actually Earths, and I'll talk about those in a second. So of the exoplanets that are known, and your book also says, I believe says that there are 450 exoplanets that were known at the time the book was written. As of mid-June of this year, of 2012, there were 778 exoplanets that had been discovered. And I would imagine at the current rate of discovery, that number is probably over 800 by the present time. The other thing is that we characterize these things as being hot or cold, depending on where they are with respect to their star, to their sun. So if they're very close to the sun, maybe within about a tenth of an astronomical unit, these things are considered to be hot, and beyond that, they might be considered to be cold. Oh, I wanted to say this. The hot exoplanets lie from about 0.01 to 0.10. I said 0.10 astronomical units, but that's kind of the outer region of that. And the cold ones are anything beyond 0.10 astronomical units up to about 10 astronomical units. So about 70% or a little bit less than that are cold Jupiters or Neptunes, and about 30% are what we would consider to be hot Jupiters, and approximately 1%, or maybe a little bit less than that, are super Earths. And as I said, even though your book says there are no Earths found, there are a couple. And again, in terms of this distribution, the other thing that I wanted to say is that when we say 70%, 30%, 1%, that's probably not entirely accurate either, because you have to understand that the larger, more massive exoplanets are much easier to find. First of all, they're going to cause a much greater perturbation or wobble of their stars than the smaller ones, like an Earth-sized planet would. That's one thing, one reason that we can see them. And also, if they're sufficiently large, it will probably be easier to see them by occultation as well. So it may be that at the time your book was written, where basically they're saying that you can't see, it's hard to see super Earths, and we don't see Earths at all because they're too small to actually create enough of these velocity fluctuations, these movements, for us to be able to measure. But we've gotten better at being able to do that, and so now we actually can see some of these things. And so to that end, I wanted to talk about a couple things. I wanted to specifically address the idea of Earths, that is exoplanets that would be the size of the Earth, and one in particular. Okay, so there is a star that is actually in the constellation Libra, and this star is called H.O. Librae, Librae. It lies some 20.3 light years from the Earth, and it's an M-type star, which is a cool star. It's a star that's perhaps 2,000 degrees, or actually it's a little bit more than that. It has a surface temperature measured at about 3,200 kelvins. It's approximately 1/3 the mass of our sun, so smaller. But what's interesting about it is that there are at least 4, and perhaps as many as 6 exoplanets that are surrounding or orbiting this particular star, Gliese 581. So Gliese 581 has stars that are planets that are designated B, C, D, E, and there may be an F and there may be a G, but those haven't been confirmed. But 581b is a Neptune-sized planet, approximately 16 Earth masses in size. But Gliese 581c, 5.3 Earth masses. There's a 581d, which is about 7, and also 581e, which is 1.9 Earths. E lies, there's a diagram in your book. I don't happen to have it. See if I could find it. Yeah, so here it is. This is on page 378. So if you look, you'll see a curve that looks sort of like this. And over here, on the x-axis is the distance from the star in astronomical units. And over here, on the other scale, we have the mass of the star in solar units, ranging from approximately down here about 0.1 up to, and we put our own star, the sun, over here. That's by definition 1.0, and then out here would be, let's say, 10.0. And we could put various objects in here. We might have out here a blue giant star, and over here we have something a little bit larger than our own sun, and then here would be the sun, and then we get down to an orange, a smaller orange object down here, and down here we'd have maybe a red dwarf. And what we could do is then we could actually look at the various exoplanets that are described in your book. And what you'll find is, if you look at our own solar system here, you've got Mercury, which is very, very close to the sun, and then you've got Venus out here, which is almost, this, by the way, this particular zone in here would be called the habitable zone or inhabitable zone. So what it's saying is, depending on the size of the star and how far away it is, there's a region in which, if that star, if we plot that, that planet, if we plot that planet in terms of how far away it is from the star and where it is, what sun is actually surrounding it, we can see, its distance from the sun. And then if it actually happens to fall in this region here, the temperatures are going to be such that we can actually have liquid water. And that's an important consideration. So where in the universe, if water was actually present, would it exist in a liquid state? Because one of the prerequisites for life as we know it is that there would have to be water, and the water, at least some of the water, would have to be in the liquid state. So over here we've got Venus, and then we've got Earth, which is right in the middle here. But Venus is actually touching this. So again, Venus, if it weren't for the runaway greenhouse effect we have, Venus would actually lie in that zone. And Mars is kind of partially in there as well. So Mars, possibly, and we're still thinking maybe there'd be some life out there. But then we've got Jupiter, Saturn, all these other things, and they're well outside of that. Well, if we actually look at the two Glieses, Gliese 581d, 581d is, their star is kind of over here in terms of temperature. So Gliese 581d is just to one side of the habitable zone. But Gliese 581c, 5.3 Earth masses. So this is D, this is Gliese 581d, and 581c, however, lies a lot closer and partially inside of the habitable zone. So sometimes this is referred to, you'll see this in popular reports concerning the finding of this particular exoplanet. Sometimes they call it the Goldilocks planet. You know, it's not too hot and it's not too cold. It's just right, and maybe there is liquid water present there. So that being the case, that still leaves us with, are there any exoplanets that are actually Earth-like in terms of their size? And the answer is yes. On December 20th, there was a report that NASA's Kepler mission had discovered the first Earth-sized planets orbiting a sun-like star outside our solar system. And this particular star is known as Kepler-20, and that's the star. And Kepler-20 is a G-type star. The letter G actually has to do with the temperature of the planet, of the star rather. We'll get to that in a later chapter. But our own star, the Sun, is also a G-type star. So Kepler-20e orbits the parent star every 6.1 days, and there's also another planet called Kepler-20f. So 20e and f. All right, so 20e is slightly smaller than Venus. It measures 0.87 times the radius of the Earth. And 20f is just slightly larger than the Earth, very slightly larger. It's 1.03 times the radius or diameter of our planet. Both planets are in this 5-planet system, and it's approximately 1,000 light years away from us in the constellation Lyra. Kepler-20, I said Kepler-20e orbits its parent every 6.1 days, and Kepler-20f orbits every 19.6 days. Well, this is great. We've now got a Earth-sized planet. The problem is that the short orbital periods mean very, very hot, inhospitable worlds. So Kepler-20f is believed to have a surface temperature of 800 degrees Fahrenheit, which would be I don't know why this is given in Fahrenheit. I guess it's for popular consumption, but it's going to be something around 400 Celsius, and it's similar to the temperature on the surface of Mercury. The surface temperature of Kepler-20e is hot enough to melt glass, and that's about 1,400 degrees Fahrenheit. So that you know, even though we now have found Earths, extrasolar Earths, we still don't have one that is actually orbiting in the right position. So here we've got a world, a possibility of a world that's in the right zone, but it's kind of massive. And to find something that looks like the Earth, we'd still want to see something that was actually in that zone. But it does. But I still want to correct the mislabeling in your book, because I mean it's not that the authors made a mistake, but at the time the book was written, this was not known. So this is a relatively recent development, something that was only discovered within the last 9 months or so. There's another planet here that also is in the habitable zone of its parent star, and this is another Kepler. This Kepler spacecraft is what is actually finding these things. So there's another star called Kepler-22, and its B star is in the habitable zone. It's likely to be too large, however, to have a rocky surface. And the other two, of course, Kepler-20e and F, are too close to their parents to actually have liquid water on their surface. So that pretty much gives us the information regarding the exoplanets. Okay, so next time what we'll talk about are our sun, and then we'll talk about stars in the following chapter. But we're now at the halfway point. So again, I will see you next week. Thank you.